Okay, now we go to the next one. Okay, now we go to the next one, right? Fundamental problem 32. So now we have a column, right? 3.6 meter long column, wooden rectangular column. Okay, this column is rectangular with this cross section of 100 millimeter and 50 millimeter, right? And the question tells you that for this wood, the E is 12 gigapascal and the condition is pin and pin, right? So because it is pin and pin, so the K is 1. Okay? And the question tells you that the yielding does not occur, so you don't have to check for yielding here. I mean, yeah. So how do you do that? Again, you need to find what is the critical buckling load, which is P critical equals to pi squared EI over KL squared. Again, KL both squared, right? The K is 1, like pin and pin. In this case, it will not affect that much. Okay, show a mistake. E is 12 gigapascal. How about I? Right. In this case, can you see that for this cross section? Okay, this cross section. This is the length, right? But the cross section, you look from the bottom or from the right, you see this rectangular cross section. You have two eyes, right? One is like this, and one is like this. It doesn't matter whether this is XX, YY, or whatever. You can let's take it as the horizontal one is XX and the vertical one is YY, right? Can you see that actually in this case your IXX and IYY are different, right? Because for the cross section, for the rectangular area, the formula is 1/12 BH cubic, isn't it? Right? For in this case, for if you take the IXX, the B is 50, the H is 100. So it will be 1/12. B is 50, H is 100. Okay? So your IXX is something. Okay? And another one is your IYY, which is 1/12. Okay? Again, not again. In this case, okay, 1/12 BH cubic, BH cube is for the rectangular area. Okay, but you have to understand this base is the one which is perpendicular to, parallel to the axis you want to find. If you define X as this, so the base will be this, right? In this case, IYY, YY is this axis, so the base is this, right? In this case, it is 100 base. The height is 50 cubic, right? So in this case, your IYY is actually 1041.67, right? Times 10 power of minus, power of 3 millimeter to power 4, right? Okay, I didn't calculate myself, but actually in this case, the IYY is smaller than IXX. Alright? I mean, you calculate yourself, but you will see that this IYY is actually smaller than IXX. The reason? What's the reason? Can you see that? The formula is kind of similar, right? The only difference is which one is the base, which one is the height, right? This height, okay, H is raised to the power of 3. So if you have higher height, you will have higher I, isn't it? So in this case, which one is higher? Will be higher. Will IXS, right? Because in this case, the height is, in this case, IX, the height is 100. IYY is 50, isn't it? So of course, when you raise 100 to the power of 3 compared to 50 to the power of 3, this one will be bigger. So your IY1 is less than IXX. Okay, in this case, which one you want to choose to put into the equation to evaluate your critical buckling load? You will use this, IYY. Why? Because actually this is the weak axis. Okay, this column, this member is weak about this YY axis compared to XX. So it will buckle about this YY axis first. Okay, so you put into the equation for P critical. Now your critical buckling load equation will be, now this is IYY, right? So P critical equals to pi squared, E is 12 gigapascal, IYY is 1041.67, 10 power of 3 into power 4, and your K is 1 times L, length is 3600 millimeter squared. So your critical buckling load here is 9.52 kilonewton. Alright, of course you can find your critical buckling stress if you want. You just have to divide this with your cross-sectional area. Alright.